In May 2023, an image of black smoke rising beside a concrete government complex appeared online. 2 minutes later, the stock market dropped $500 billion. The explosion never happened. It was a fabricated attack on the Pentagon, generated entirely by artificial intelligence and distributed through what appeared to be a verified news account. A convincing audio clip of Barack Obama demonstrated how a single person's voice could be cloned and weaponized to say things they never uttered. This kind of disruption naturally brings up fears of a conscious, malevolent cyborg assassin plotting our destruction. But that science fiction scenario obscures the actual mechanism at work. Computers haven't suddenly developed a mind of their own. Instead, they have mastered a deeply human mathematical trait, the ability to recognize and predict patterns. To navigate an era where our digital reality can be manipulated so easily, we have to look under the hood of this pattern recognition engine, because the exact same math responsible for those deepfakes is currently being used to save lives. In the 1990s, artificial intelligence relied on strict, human-coded rules. When IBM's Deep Blue defeated the world chess champion, it did so by calculating millions of rigid, predefined moves per second. Today's models abandon those strict rules. Researchers now build artificial neural networks, structures modeled on the interconnected web of neurons inside the human brain. These networks learn by ingesting massive datasets. When the system achieves a successful outcome, it adjusts the numerical weights within its code to strengthen the connections that led to that success. When it makes a mistake, a process called backpropagation sends a signal backward through the network, actively weakening the pathways that caused the error. The machine is no longer executing a specific task written by a human. It is continuously training itself, evaluating millions of examples until it can reliably predict the next logical piece of data. By breaking down medical scans into tiny visual patterns, convolutional neural networks identify microscopic anomalies representing early-stage lung cancer years before human doctors perceive them. The same mathematical logic extends to the building blocks of biology. AI has mapped how millions of amino acid chains fold into specific three-dimensional shapes, unlocking the structure of nearly every protein known to science. With these structures mapped, generative models design completely new synthetic drug molecules, engineered to dock into disease-causing proteins and inhibit their function. Out in the physical world, neural networks are monitoring hundreds of remote mountaintop cameras, scanning the landscape to identify the faint plumes of nascent wildfires so dispatchers can respond before they spread. Curing early-stage disease, accelerating drug design, and stopping environmental catastrophes all rely on a single shared capability: ingesting historical data, identifying the hidden patterns, and projecting them forward. But that exact same architecture can be inverted. In generative adversarial networks, two algorithms are pitted against each other. One generates fake images, and the other attempts to spot the errors, iterating thousands of times until the forgery is flawless. Diffusion models take this a step further. They learn by intentionally corrupting millions of real images into pure static noise. Once the software understands how to turn a photo into nothing, it reverses the process, building a photorealistic fake image from scratch. This reverse engineering process works on sound, too. By identifying the unique acoustic patterns in just 90 seconds of reference audio, an algorithm can clone a human voice and make it say anything. The neural network isolating a tumor in a CT scan and the network generating a fake explosion at the Pentagon share the exact same core mathematical DNA. The mechanism that decodes physical biology is the same one used to dismantle shared digital reality. While the digital world generates seamless illusions, applying artificial intelligence in physical space reveals a much slower reality. Integrating AI into a myoelectric prosthetic arm requires intense physical friction. These robotic limbs use Bayesian classification models to read the faint electrical signals generated by a person's nervous system. The software takes those signals and sorts them into buckets corresponding to commands like open, close, or rotate. The technology is far from perfect. Out in the real world, the AI frequently misinterprets the user's physical intentions, twitching or dropping objects as it tries to guess the correct movement. This machine learning algorithm demands tedious, deliberate repetition. Both the human nervous system and the AI must adapt to each other over weeks of training. Real-world AI functions as a dependent collaborative tool, requiring intense human input and training to achieve even basic functionality. We cannot simply pull the plug on this technology. The commercial momentum driving artificial intelligence is projected to create a multi-trillion-dollar economic impact by the end of the decade. Governments worldwide are racing to institute regulatory guardrails, trying to mandate testing and security standards to mitigate the risks of such rapid deployment. But laws and detection software can only do so much. The ultimate defense against digital manipulation requires a permanent shift in how we interact with media. As machines refine their ability to perfectly mimic our voices and our images, we have to adopt a new baseline philosophy for everything we see and hear. Trust, but always verify.